We are back once again, day 38. Actually, I have to change this because it says day 37, but it's day 38. Reflections on yesterday. I mean, we did quite a few problems yesterday. I mean, it was probably the actual recorded time is only, I think, an hour and 45 minutes, but also it's probably a good thing to say I actually do more practice off recording, but it's more interspersed, like, after the day, like, at nighttime. So it's kind of in between, maybe watching a show or eating dinner or something like that. So there's more practice done than what's recorded. But yesterday I was, we're still sick. It is what it is. But I think I did like an hour and a half. And earlier I did like, I had already done like 2 hours. So it was already late at night. So it's like 4 total hours. And then I was like, I'm not doing another 20 minutes. And yeah, so we ended a little early, but even then we shot way past the goal of an hour and a half anyway, since we did like 3.5 hours, almost 4.5 hours actually. But it is what it is. Reflections on yesterday's problems. I mean, we were frying. I mean, I don't even remember the problems that I did yesterday. Is that a negative reflection of the practicing style? Who knows, right? Ideally, the work we're doing is being elaboratively encoded right into our brains as knowledge that we can't explain. So ideally, that would probably mean we can't explain it, right? And so I don't actually know which problems I was doing, but I do know that what I'm learning from the problems is kind of being osmosis into these decision trees that hopefully can be retained, or maintenance can be done upon them by doing similar problems, reusing those solutions for other problems. That being said, I do remember we tried to do product of array except self, and we got fried by this problem. I mean, the initial intuition makes sense, but I mean, you're kind of blocked by left by not being able to use division. So in the end, we ran into some other issues with that. We never got to try writing oranges, so we stopped on. Course schedule is still on the back burner. Other reflections on the progress so far, I was doing some thinking, and I think ever since day 10 or 11, we've been kind of hovering at around an hour and a half done daily. And I think that's pretty cool. And I was trying to think of how many hours I've actually spent doing this. And at this point, I mean, you do like around 38 days times 1.5. It's like 55 hours or something like that. Not the best, but also have to note that there was a lot more, there's other practice not included. I would say all in all, we've probably done about, if what I said earlier was about 50, what did I say, like 48 or 55 hours, I would say total practice done, if I really had to put a finger on it, I would probably say it's around like 70, maybe 65. That being said, if this is 65, I mean, times 2, like 125 must be even better, right? So I'm kind of interested to see what that would be like. And so actually, we're probably at more than that, because I just said we do more than, well, not every, the minimum is an hour and a half a day at this point. But most recently, we've been doing more than that, after we do the hour and a half, just between working out, maybe after dinner. So honestly, a few days in there. So I would say our original statement, yeah, it's probably around 65 or 70. So if we could probably double that or triple that, then I think we'd be good. And I'm actually proud that we switched to and reflections on using the grind 75. I'm actually happy I switched to the grind 75. Initially, we were just going down most frequent problems, and I think both approaches are good, right? Because if someone tells you need to do these problems, you think, oh man, I have to do these problems, right? You start with the first problem, you can't do it, you want to die. At least that's what happened to me, right? Because in the beginning, I mean, a lot of these problems will say easy, and it'll feel unsolvable. I mean, you'll feel like you don't know what you're doing, like you never programmed. And I think that's probably also why a lot of people have problems with these types of methods of rating candidates' experiences and stuff like that. But it's besides the point. What I'm trying to get at is that originally I was working on just doing problems even easier than the problems listed here. And what that allowed me to do is just build confidence and kind of get a stride going. So it's kind of like if you wanted to run every day, but you can't run. And so what I opted to do instead was to walk a minute every day. And walking a minute every day, or I guess sprinting for a minute every day, or 30 seconds every day, kind of allowed me to build the confidence. So at around like day 40 or 50, I was like, I could probably start running for 15 or 20 minutes. And so that's when we switched to the grind 75. So not upset about it, but the problems do cover a good range of topics. And so I do in a strange way feel like I'm grasping the patterns here, especially in terms of the graph and tree problems. There seems to be a cheat code I found, which is kind of like using a level order breadth, like a level order iteration iteratively. Then you can layer a depth first search algorithm on top. Kind of a cheat code for tree problems. Definitely not optimal time or space complexity, but it allows you to get to a solution that most times, I mean, I wouldn't be able to get to without it. So I think that's useful, right? Credit to be given where credit is earned. But yeah, ideally I'd like to finish I'd like to just finish as a personal goal. I'd like to finish all 75 of these problems as like a short-term goal. And then long-term goal, I want to finish all LeetCode problems. Now you don't really get a medal. You don't really get flown out to California by Mark Zuckerberg or Jeff Bezos for finishing all these problems. But I think it's just a cool thing to do. And for some reason I get enamored with setting ridiculous goals and just having something to run after. So I'm just going to really try and get all these problems done. And so that being said, there's a standard to which you want these problems to be completed at. But I will say solving one, for example, does sort of count. It is what it is. So I think what I'm going to do is try to progress through as much as I can, right? And for example, some that are giving me issues are course schedule and product of, actually mostly course schedule. I think we intuited the solution for product of array except self, but we had trouble implementing it, or I wasn't confident that it was a potential, the potential pathway that I had generated for a solution I wasn't confident in, therefore I didn't really give it enough juice to really see if it was worth pursuing. Turns out that was the optimal solution. It's probably a confidence area there as well. So we're going to keep pushing. We have course schedule on the back burner, product of array except self on the back burner. We have rotting oranges, and I'll probably do rotting oranges and then product of array except self. And if we have time, we'll do search in rotated sorted array. But yeah, so that's what we'll do. And so we'll start with rotting oranges for now. So I'm just going to jump into it. At the same time, make sure to join the Hyperbolic Coding Chamber Discord. Thousands upon thousands of people joining every day. Jeff Bezos just joined yesterday, and he's giving people a lot of tips and easy cheat codes. So you might want to join and get those tips before it's too late. And yeah, we're just going to jump into the first problem, rotting oranges. So you are given an M by N grid where each cell can have one of three values. 0 representing an empty cell, 1 representing a fresh orange, or 2 representing a rotten orange. Every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. So we're returning a number and we're given an array, a matrix of numbers basically. So example 1, let's try and map what we just read to the example. Given an M by N grid, so this is the M by N grid, where each cell can have one of three values. Empty cell, fresh orange, or rotten orange. Every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So I think the intuition here is that being next to a rotten fruit makes you rotten. And so that's what they're kind of using for this problem. They want us to return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. So on minute 1, we have 2, 1, 1. 2 means we have a rotten orange. 1 is a fresh orange. 1 is a fresh orange. Fresh, fresh, empty, empty, fresh, fresh. Okay. IC, and then the output is 4, because since this one is rotten, we have to pretty much check any 4 directionally connected rotten orange and make that rotten. On the next iteration, we do the same. On the next iteration, right, we make it even more 4 directionally rotten, and then at the end, minute 4, all of them will be rotten. Okay, so I think I'm understanding. So we have 2. So in this second example, we have 2, 1, 1, 0, 1, 1, right? And if we were to layer this all together, just put this right here, we'd have 2, 1, 1, 0, 1, 1, 1, 0, 1. And they're saying the orange in the bottom left corner, right? So this orange in the bottom left corner is never rotten. It's not 4 directionally connected to any other rotten orange. So we have to return -1. And since there are already no fresh oranges at minute 0, the answer is just 0. So we have actually a lot of interesting cases given here. Very many interesting cases. Our first case being one where the example actually plays out perfectly and it's actually possible to make all the fruits rotten. And then later on we have another case where it's impossible. Another case we could also generate where it's impossible is if the entire array is empty, if the entire matrix is empty, then it's not possible, right? And so it's not possible, or the number we return, right, would have to be -1, since it's not possible for all the fruits to be rotten since there are no fruits. Example 3 shows us that even if there are fruits, if they're all already rotten, then there's no point. Then there's no point. And there's no point in checking, right? If we can, or since there's already no rotten fruit, since all the fruit is already rotten, right? The minute where we can minimum number of minutes that must elapse until no cell has a fresh orange, or until all cells have a rotten orange, would be 0. So just to generate some ideas or on data structures or methods we could use, I'm thinking we're going to want a way to know in relatively constant time whether or not all the fruits have become rotten. That being said, I think we could do this by, if we had a variable, right, called oranges, right? And these are oranges that are fresh, right? And we could get this, right, by iterating over the matrix and just counting all the fruit, right, or all the numbers that equal 1. These would be fresh fruits. Right, now if the fresh fruits by default, right, if oranges equals 0, if this fresh fruit already equals 0, right, then we want to return 0. Right, so this handles our last case here, right, where all the fruit is already rotten. There's no point, right? There's no oranges to actually turn. Right, but now we need to handle the second case, right? The orange in the bottom left corner is never rotten because rotting only happens 4 directionally. Right, so I'm thinking we're going to need a function that could likely do a depth first search and check if it's possible to rot more. Right? Like, is possible to rot, right? And if this ever returns false, right, then we can return, or if it ever returns false, right, if is not possible to rot, right, then we want to return -1. that could handle our second case. And then our main case is that we'll basically want this to go through. So thought I was gonna sneeze there, but so we'll have, and so basically we basically want to do basically a time series simulation on this matrix. And I'm thinking one way we could do that is potentially with a while loop. If we had a while loop, right, and this while loop would run, right, while it's possible to rot, right? The first thing we check, right, is if, right, this while would run, right, if oranges is greater than 0, right, and I'm actually thinking about if oranges equals 0 here. That helps us on this first case, but what if okay, so yeah, we'll say while oranges is greater than 0, right, and, right, it's possible, I don't know, while orange is greater than 0, right, and so we'll be in this while loop with our time series, right, and so what we want to do, right, is say, right, so we can actually change is, okay, so now this is really coming together. We can change is possible to rot to just a rot function, right? And this rot function returns num rotted. It's going to return the number of fruit it rotted, right? And if rot ever equals 0, right, then what we want to do is know that it's not going to be possible to get, if rot equals 0, right, and oranges, right, or this oranges is greater than 0, right, so if rot equals 0, right, it means oranges is also greater than 0, so that would mean that basically it's not possible to get the minimum number of minutes that must elapse until all the fruit are rotten, so we'd have to return 0. And we'll just call rotted, right? And then we'll always do oranges minus equal rotted, right? And so the other thing we want to work on, right, is actually getting the minimum number of minutes, right? So we'll have mins, right? We could let this equal to 0, right? And since we were able to do some work, right, oranges minus equal rotted, we'll say mins, right, plus equal 1. So, right, given a, and we're going to want to do this, maybe we can actually do this from multiple angles, right? So in this example, there's only one rotting fruit, right? But many rotting fruit can rot multiple fruit at once. So we're going to want to call this rotted function several times. Right? So we'll say several calls, and we'll get jump to the implementation really too soon. So running out of a bit of time here, but just to map out the general idea, we'll do mins plus equal 1. Right? We'll get all the rotted, do orange minus equal rotted, mins plus equal 1. Now as soon as oranges so this case right here, rotted equals 0 is going to handle where we can't rot any more fruit. We want to return 0, right? Otherwise, right, if oranges is not greater than 0, then it must be 0, right, or less than 0. Now, if that's the case, oh, that's my bad. Not that we don't want to return 0. We want to return -1, right? Because it's not possible to rot any more oranges. right? Now we have to actually figure out when we can return 0, right? When we do return 0 on the first case up here, right, is when we start. And then the thing is out here we'll return mins, right? Because that would be the first minute where all the fruit is rotted, right? So let's jump into the implementation here. We would have let oranges, right, equal 0, right? And we have to calculate all the oranges, right? So we'll say for let I equals, and we'll just do it like this, for let row equals 0, row is less than grid dot length, right? Row plus plus. We'll do row plus plus. We'll do row plus plus, right? And then we'll change row here to column. And I feel like this is a little hard to read. We'll do call is less than grid sub row dot length, and then we'll do call plus plus, right? And so now we have this scenario, we have this for loop, right? And when do we have an actual orange, right? It is when the number at the index represents a 1. So we'll say if grid sub row, right, sub call equals 1, right? Then we're going to do oranges plus equal 1. So now we have the number of oranges, right? And we want to say, right, if oranges, right, from the beginning is already equal to 0, right, then there's nothing that the minimum minutes that must elapse for all the fruit to be rotten is 0, right? Because we're already at that point. So we can just return 0. Right, and we have mins equals 0, right? I'm going to say while, right, oranges is greater than 0, right? And we still have to define this rot function, right? We're going to do several calls, right? And since we're going to do several calls, right, basically we're going to have to iterate through the map again. So the time complexity on this what looks a little rough right now. And so to do these several calls of rot, right, we're going to need rotted, which is going to be equal to 0, right? And then we're going to say if grid sub row sub call, right, equals a rotten orange, right, which is a rotten orange, right, which is equal to 2, right, then we're going to want to say rot nearby, right, for row for grid, row, and call, right, and it's going to be rotted plus equal rot nearby, right? And if rotted equals 0, right, after doing all that, right, then we're going to want to return -1 because we can't rot all the fruit. But I'm wondering actually now how many calls, if we do it this way, we could do multiple calls, right? We do 1x here, right? We do bottom and right, then we go to the next, but this is actually a different minute already. So when we rot new fruit, we're actually saying that it can't be rotted on the same iteration. Only the fruit that have been rotted on the current iteration, or only the pre-rotted food can rot the nearby food. So what I mean by that is at this x, right, on the next minute we actually rot right and left, right? But if you were to imagine this as the code running in its current state, we'd rot right and left, and then we'd go to the next index, which would actually be 2 because it's rotted. And then that would actually be a problem, right? Because we'd actually be rotting in the same iteration, which we actually can't do. So I'm wondering, so we could definitely do more than one rot at the same time. As we see in this iteration, right? This node goes down, and actually I wish we had one more example to test, but I'm assuming that this node, it looks like this node right here, which is this one, rots the right one and the bottom one, but potentially it also looks like this node could rot the right one, right? And this top one right here could rot the right one. So that being the case, rot nearby is going to have to be special so as not to get us in trouble. So we'll call this function rot nearby. It's going to take the grid, right, which is just going to be this numbers matrix of numbers. We're going to take the row that we're interested in as well as the column that we're interested in. And so when we rot nearby, we actually want to check up, down, left, and right. We want to check those 4 directions, right? But we don't want to do it more than once, because if we call rot nearby again, it's going to keep going, and that's not exactly what we want. We want rot nearby to just check these 4 directions. So we could say if grid, right, sub r, right, and to go up we do -1, right, sub c, right. So if this value exists, or I mean, if this value actually equals an orange, right, that's not rotten, right, then we want to rot it, right, and the value that is an actual orange would actually be 1, right. Then we're going to want to rot this location. That'd be r -1, right. C would get the value of 2. And this, we still have to fix this pre-rot problem, right? Because at this rate, we would run multiple times, and we kind of want to avoid that. So when we call rot nearby, right, we would change this node to rotten and this node to rotten. But on that same iteration, right, we'd go to the next column, and it would equal to 2, right? So we'd pretty much rot the whole entire matrix in this first for loop, which is kind of what we want to avoid, and we could probably fix that with a visited set. So if we've rotted a particular node on this set, we actually want to exclude it from being called in this current iteration. And so what we'll do is we'll check those 4 nearby directions, do this 4 total times. So you want to check below us as well, and if it equals 1, then we want to change it to rotten, right? And we want to check behind us, right, in front of us and behind us, right, and we'll change these right here. So we'll do +1, -1 would equal 2, and so rot nearby here actually does make good sense. The only problem being we probably have to expand this just a little bit, because the amount that is rotted we actually have to return. So we want to do basically multiple lines here, and we could streamline this function with, we could streamline this function with a for loop and keep iterating over. This would also simplify calculating rotted, but we only have 8 minutes left on this problem. actually might just be easier to do it now. So we'll say directions is going to be an array of tuples, right? And it's just going to be 1, 0, right, for below us, right? -1, 0 for above us, right? Then we'll have 0, right, 1 for right, and then 0, -1 for the other. And then for here, we can say for const direction of directions, you can just say if grid xy of direction. So we'll extract that tuple out. We'll say if grid sub r plus x, right, and c plus y, right, equals 1, right, and we can actually string this whole thing together. Do r plus x, right, sub c plus y equals 2, and then do rotted plus equal 1, and we can remove all of this and return rotted. So this doesn't actually look so bad yet. And x and y aren't very good variable names, but they kind of get the idea across. So we change it to 2 to rotted, and then we do rotted plus equal 1. And then to avoid rotting in multiple to avoid rotting our entire matrix in one iteration, we will use a set, right, which is going to be redeclared on every iteration. And the goal of this set would be to disallow us from rotting any new any new rotten fruit that we create, right? So say if grid sub row sub call, so for each iteration we'll have a key, right, which is just going to be the row and the column, right? And we're going to say if set, right, doesn't have the key, if the set doesn't have the key, right, and it equals 2, then rot, right? And so a rot nearby, but we actually have to return which ones we rotted. And we could do that. So instead of returning a number, we could just return an array of tuples, right? And then we could just count the number of tuples as the number that has actually been rotted. And so to do that, we'd have rotted, right, which we change to an array. So doing rotted plus equals 1, we do rotted dot push, right, r plus x, right, and c plus y, and then we would return rotted. And then to actually count like we were doing before, we could just do and we'll actually be redeclaring this, but we'll just say const rotted equals rot nearby, and then we can actually change we can leave rotted here, and what we'll do is we'll set it equal to rot nearby, but instead of it equaling 0, we'll equal an array. And then for const cell of rotted, basically, we're going to want to add each one to the set. So we'll do set dot add cell sub sub 0, right, and cell sub 1, right, and we're going to say, hey, right, ignore those, and on the next iteration we will ignore it, which ends up working out. And then if rotted equals 0, we'll return -1. So let's make sure this makes sense for the first example. So we iterate through the rows and the columns, right? Grid sub row dot length call plus plus. Now if it equals a regular orange, we count it, right? We should get 6 total oranges. Oranges doesn't equal 0, and our mins equal 0. 6 is greater than 0, right? So we're going to create a new set with rotted, iterate through the entire matrix again, right? And if our set doesn't have a key, right, and we're going to be at 0, 0, it doesn't have a key for 0, 0, and grid sub row sub call equals 2, which is it does, right? Then we're going to set rotted equal to rot nearby. So we're going to do rot nearby row call. Right, our directions are 1, 0, -1, -1, 0, 0, 1, 0, -1. So we're gonna have 0, 0. We're gonna do 0 plus 1 and go down, right? With C plus 5, which is 0, which is gonna keep us in the same column. It does equal 1, right? And so we're going to rot this fruit, right? We're going to rot this fruit, and then we're going to push it as a fruit, the cells that we just rotted, right? It's 1, 0. Then we're going to check above us. We can't do that. We're going to check in front of us, which we can do, rot that as well, right? We can't rot behind us, so we actually return 2 for rotted here, right? We actually get that array, right? And then for the cell of rotted, right, we add them each to the set. We go to the next one, right, and we actually can't rot those fruit, and we keep going, iterate through the entire matrix. Rotted does not equal 0, it equals 2, so we don't quit, right? We know it's still possible. And then we do oranges minus equal rotted. And then we do mins plus equal 1. I think what I'm also noticing here is that mins is going to have to start at 1. Otherwise our value will be wrong. So let's try this. Hopefully we don't get any syntax errors. So line 45, rotted was a variable. It's an array. What we want to say is if rotted.length equals 0, we're going to do rotted.oranges minus equal rotted.length. I think that should be our both errors on 45 and 48. So we actually return -1, which is interesting. We only return -1 when rotted.length equals 0. Okay, so we're not rotting any fruit apparently. So if the set doesn't have the key, set does not have the key for 0, 0 because it's a new set. Grid sub row sub call equals 2. Then we're setting rotted equal to rot nearby, grid sub row sub call. And we should be able to do const x of y of directions. R plus x, c plus y equals 2. Then we push onto these tuples. So I think the first thing we would check is if the output, what we're getting for the output of rotted and for this particular row and column, so we're getting 2, and yeah, so we are routing 2. This is perfect. We're routing 2. Well, 2 we're routing is at index 1, 0 and 0, 1. And then plus plus call equals calls less than grid sub row length call plus plus. So grid sub row call equals 2. And so we actually can't rot any fruit. So on this first iteration, we rot 2 fruit, which is fine. On this next iteration, Apparently we can't rot any fruit. I guess to double check, because we're starting at 0, 0 again, which means we must be going to the next loop. If we're going to the next loop, that means we're getting through it at least once. We're starting at 0, 0. We didn't rot. I see what's going on. We're not propagating the value. Rotted should store the total rotted for the entire iteration through the matrix. Right now, it's pretty much reloading the value every time. So what we do want to do is actually set rotted equal to rotted dot concat with rot nearby. And so we're actually getting 5. Maybe we were wrong to start it at 1 originally, and we should be setting it to 0. So let's try with a bit more of a let's try it with our case, which should return 0, should return -1 here. Okay, and let's try with this case, which should give us 0. Okay, well, let's try and remove this console.log and see if we can get through. Oh, so it does work. Okay, so this looks like 34 minutes, and we had a minor issue. It looks like the goal for this one, the time complexity of this is for each cell, right? We're going to do the worst case, right? Because for each cell, if a cell is a rotten orange, right? We have multiple rotten oranges. If we have a matrix, we have multiple rotten oranges. As we're iterating through the matrix, right, it's going to be m by n operations, and each m by n operation triggers a function which checks for total indices. And so for each cell, given a starting cell, right, our worst case would probably be that a cell, if a cell has all oranges, then our worst case is that a cell, the entirety of the matrix is filled with oranges, because we could only rot nearby matrix cells. And so it would kind of be like we could slowly change the left hand side from rotten and kind of slide it over to the right hand side, which would be fresh, eventually making them all rotten. But the number of operations here, I would say we're doing m by n, but m by n, but for every cell. Which I think turns out to be linked to the number of, that's this one's a tough one to tell the time complexity. The space complexity is constant space, because in the worst case, I mean, we are creating some space for the set, but in the worst case, the memory we use for the set is ephemeral. It only holds the oranges we change, which shouldn't be too many. But in the worst case, how many oranges could we change? If we look at this, we change 1. So in this case, if we imagine, right, that these bottom 3 right here are not rotten, right, we would check rot for basically every single, right, so we check rot for every single rotten orange, regardless of if it's possible for it to actually rot any of its nearby neighbors, any of its neighbors. So basically, if we have, let's just say 6 total oranges. You run an iteration. Now we have 7. Now we have 4. Now we have 2. Now we have 1. It looks like maybe this would be the worst case. Could be in the case it kind of seems like number of operations we have, how fast can it decrease? The best case scenario for our algorithm is that all the oranges are already rotten. Second best case is that only one of the oranges isn't rotten and it's right next to another one. I'll say the worst case is that the matrix is filled with all fresh oranges and one rotten orange. And then from there, I think it would take definitely at least minimum m by n time, but m by n to the m by n. Is that what we're getting at here? In addition to 2D grids, these two algorithms are often applied to problems associated with tree or graph data structures. One can see that BFS would be a better fit. Because the process of rotting could be explained perfectly with the BFS procedure, the rotten oranges will contaminate their neighbors first before the contamination propagates to other fresh oranges that are farther away. Argument of BFS, one can afford to explore a card of Q and stack, which covers this subject. However, it will be more intuitive to visualize the rotting process with a graph data structure where each node represents a cell, and the edge between two nodes indicates that the given two cells are adjacent to each other. In the above graph, pun intended, as we can see, starting from the top right in orange, the contamination would propagate layer by layer or level by level till it reaches the farthest fresh oranges. The number of minutes that are elapsed would be equivalent to the number of levels in the graph that we traverse during propagation. One of the most distinguished code patterns in BFS algorithms is that we often use a queue data structure to keep track of the candidates that we need to visit during the process. The main algorithm is built around a loop iterating through the queue. At each iteration, we pop out an element from the head of the queue, then we do some particular process with the popped element. We then append neighbors of the popped element into the queue to keep the BFS process running. Here are some sample implementations. So they end up building, they have a queue, they end up building a queue of rotten oranges. No, they actually end up duplicating the grid. No, I mean, they have grid sparse sub C. Oh yeah, they pretty much have a queue of the rotten oranges as well as a number of fresh oranges. And we mark the round levels, so they put a queue, put another element at the end, start the rotting process via BFS. They have an array of directions that we can use. And then we'll have while the queue is not empty, they'll take an element off of the front. If the row equals -1, we finish one round of processing, minutes elapsed plus equal 1. Queue, to avoid the endless loop, we add a 1. Else this is a rotten orange, then it would contaminate its neighbors. So for in directions, I think what they're basically doing is instead of iterating over the entire matrix every single time, they're just keeping a queue of rotten oranges That way we don't have to keep visiting nodes that are fresh. And so that's one way to optimize it, but I feel like that would mean that they're right, and even after they rot in orange, they add it to the queue. So I'm curious what the time complexity of this. And do they also use visited? Because we had to make sure we don't visit nodes that we just rotted. So they didn't do that. But as one notices, rather than using the visit table, we reuse the input grid to keep track of our visits. We are altering the status of the input grid in place. Current values, rather than referring to the visited table. There's a lot of optimization time complexity O of n, where n is the size of the grid. Addition values for the queue, which would take linear time. Then we run the BFS process on the queue, which in the worst case would enumerate all the cells in the grid once, only once, therefore it takes O of n time. That was mine O of n. Well, I wonder how many total runs we have an in-place spread first search. This, I was thinking that the worst case would be something like this, but it felt impossible to explain. And as the size of the input grid. So let's say the time complexity of this okay, that's actually not bad for first try. That was pretty good. So let's try search in rotated sorted array. So there's an integer array nums. There's an integer array nums sorted in ascending order with distinct values. Distinct values is important. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index k. 1 is less than or equal to k, so k is always not the first element, but the second element to the end, such that the resulting array is num sub k, k plus 1, num sub 0. For example, 0 index 0, 1, 2, 3, 4, 5, 6, 7 might be rotated at pivot index 3. 0, 1, 2, 3, where the pivot index becomes the first element all the way into the end until it reaches that value and restarts. Given the array nums after the possible rotation and an integer target, return the given the array nums after the possible rotation, given the array nums after the possible rotation and an integer target, return the index of target. If it is in nums, it is in nums, or -1 if it is not in nums. You must write an algorithm with log of n runtime complexity. So looks like our array are at target 0. Our array has been pivoted right between 4 at 4, so we have going to 2. We had a sorted array, it's been pivoted at 4. Right now we want to find our target, check if our target number, which is 0, exists, return its index. That index would be 4, 0, 1, 2, 3, 4. We have another one, 4, 5, 6, 7, 0. Our target is number 3. Want to know if the number 3 exists in our input. It does not. Are they all distinct? It is distinct. So I don't know if I'm underestimating the problem, but you must write an algorithm in log n. So if we have to write it in log n, then we can't iterate through the array and create a set, right? And if we create that set, then what we could do is just return in this map, we could just create a mapping of number to index, and we could just return map.get target if it exists, otherwise -1. Do log of n, so I'm thinking binary search. And maybe we can do it with, I'm thinking binary search with 3 pointers. So if we have this array that they've given us, 4, 5, 6, 7, 0, 1, 2, and our t equals 0, right? We could calculate our pivot, right? And our pivot it's actually tough. There's a few linear time ways you could do this. I was thinking that we could resort the array, pretty much unrotate it, binary search, find the index, and then also check what the number or the index that was rotated to the front and just subtract it from our goal index. That would not be linear time. We want log of n. How can we do a better binary search? So we have 0. So we'd have, if we had a binary search, our left pointer would be 4, our center would be our center would be 7. So we'd have 0, 1, 2, 3, 4, 5, 6. Middle element would be 0, 1, 2, 3, which would be 7. So we have 4, 7, and 2. And basically, we'd want to do a binary search for whichever one it exists. Since it's been sorted, we could just do the binary search in between them. But I think this only works when our pivot, which is not even our pivot, when our center number when we're able to find the center number. So we need a way to find, well, if it's been rotated, if we always take the number at the center, let's say we rotate this array in a different way. Right, let's just say it's now 6, 7, 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. If we take the center, right, the center is now actually 1. So that doesn't, wait, I think we have 0, 1. There's no 3. And so we need a way to quickly find the center. But we need a way to find the lowest index in the array. The lowest index in the array would help us to be able to do a binary search. And since it's rotated, our search would still be log of n. So the naive approach, I guess, or the approach that we could work with is binary search to find lowest number or lowest index. And we actually can't binary search to find our lowest index because we can't binary search to find our lowest index because we need the array to be sorted first. We're all distinct. Maybe we could binary search anyway. Or in another sense, so if we said we're looking for 0 and we're at 6 and 7, right? We could say is 0 greater than, so we're at 6 and 7, right? We're saying is 0 greater than 6 and 7? No. It is not. Or basically the number we're looking for, we want to be less than it. So if we're looking for 0 here and we're at 4, we want to keep incrementing. You could increment by half, right? And if we increment by half, we'd be at 7. We'd say, is 7 greater than 0? And it still is, so we'd increment. Can't increment by another half. Well, we could, and we'll say we're at 2. Well, now 0 is greater than 2. Well, 0 is less than 2, which is perfect. Now we can decrease by half, right? And then we'll be at 0. So maybe we could try that. So the way this would work is we would start at an index. So we'd start an index, right? That index would be let's just say I equals 0, right? And we're gonna say, right, if num sub I, right, is greater, so our number is 6, right? Is num sub I greater than our target? Well, it is, right? And if that's the case, then we want to move forward half the length of the array. So how could we do that? We could say length over 2, 0, 1, 2, 3. Well, based on where we are, right, we're at 0, right? Now it basically end up being 0, 1, 2, 3, 4, 5, 6. So 0 plus 3 is index 3, 0, 1, 2, 3. So you just say I plus equal nums dot length over 2 floored. And if we floor it, we should keep our integer. And so now it'd be I equals 0, 1, 2, 3. So now I is actually going to be equal to 3, right? And we'll have our else if, right? If num sub I is less than 0, is less than our target, and we had 0 here, what we mean is target. So if num sub I, which is 1 less than our target? No. Is num sub I greater than our target? Yes. Num sub I is still greater than our target, so we would add half. So it would still be greater than it, but it's tough because now we're actually past it, and passing it is still very much possible. So this doesn't exactly work either. So what if we went back to our 3-pointer approach? We'd have 4, 7, and 2, and we could say, is 0 between 4 and 7 or 7 and 2? Zero is definitely between 7 and 2 somehow. So we know 7 is the end of our array. What if we were looking for 5? Well, we could tell 0 is a tough one. So what we can do is, what if we have 3 pointers? We remove this. We'll do 3 pointers, and what we'll do is we'll move the 3 pointers based on what's going on. So we start at left equals let left equals 0, right? We'll have right equals nums dot length minus 1, and then we'll have let mid, right, equal to the math dot floor of nums dot length over 2, right? So now we'll have our values, and basically want to know which way to go, right? And we can say, right, we'll basically always just be moving left and right, but changing it depending on which is more likely to be where we want to go. So we'll say while left is less than right, and it'll work just like the original binary search but kind of modified. And then how do we know when we want to move it, right? We'll say if num sub I is between the first range, and our first range is 4 to 7, right? So say if num sub I, right, is if we have left, right, we'll have nums sub left, right? And we'll say if num sub left is greater, or if num sub left is less than num sub I, and num sub right, actually not num sub right, actually num sub mid, and num sub mid is greater than, oh, not num sub I, it would actually be target. So if num sub left, which is 4 greater than 0, is 4 less than 0? No, right? So it's not in the range, right? And num sub mid, right, which is 7 greater than 0? It is, right? But neither of those are true, so let's go into our else, right? Basically means we want to go to the other range instead. The other range is 7 and 2. So since we're in 7 and 2, we want to work, right? We want to set left equal to mid, right, plus 1, right? And plus 1 would actually take left equal to 0, right, which is our goal number, and right would actually still be 2, and our mid, right, our new mid would have to be left plus the math dot floor of right minus left over 2. And so we'd have 6, 0, 1, 2, 3, 4. We'd have 6 minus 2, which is 2, right, over 2, which is 1, plus left, right? And what was left? 1, 2, 0, 1, 2, 3, 4. So we had 5, right? So we'd have 4, 5, and 6. And left is still less than right. And then we'd say, okay, well, is nums sub left, right? If num sub left is less than target, right? And is num sub left, is 0 less than target? No. it is not if nums, we want to do equals, right? So if num sub left is less than or equal to target and num sub min is greater than or equal to target, right? So if num sub left is less than or equal to target, which it is, and num sub mid, right, which is 1, is greater than or equal to target, which it is, right, we actually want to move, I'll make this a little bit bigger, we actually want to move right equal to mid minus 1. And if we do that, then we'll have 0 and 1, so we'll be really close, right? And then our new mid, right, which we can actually at this point just place out here since we're going to copy for both, right? Since we do right equals mid minus 1, we're at 4 and 5 basically. We do 5 minus 4 is 1 over 2, 0, 1, 5, 4 is 0, and left is going to be 5. So 0, 1, 2, 3, 4, 5. Wait. So do right equals mid minus 1. Mid was equal to 1, which was 5. We do minus 1. No, right was equal to 2, which was 6. So we do 6 minus 1, we get 5. But if it's between this range, we want to set it to mid minus 1. And mid was actually 5, so right minus equal mid minus 1 would actually give us 4. So left and right would be 4. And so we can actually do this. We'll say left is less than or equal to right. Then we can have our final case. We'll say if nums sub mid equals target, right, then we can return mid, which seems to make sense. We could return mid here because when they're both the same, we do right minus left is 0 divided by 2 is 0 plus left, which is going to be 4, and then we should get it. And if we can't find it, we can return negative 1. So let's try it. So it works on the first time, and it fails on this one. So we actually return negative 1. So left equals 0 here and right equals 1. Let's say 0 is less than 1, right? And we'll calculate the mid. The mid is going to be nums.length over 2, right? Is floor at 0. We're going to say if num sub mid, which is 0, equal target. Wait, so we should actually return mid here. Nums sub mid, nums.length, which is 2, over 2. Over 2 is 1. Over 2 is 1. Even so, it should be able to handle that. And then we'll say if num sub left, which is 3, is 3 less than or equal to target, is 3 less than or equal to 3? Yes. And is 1 greater than or equal to 3? No. So I'm wondering actually if we even need this secondary case right here. What if we commented it out? I'm actually not certain that we need, maybe all we need is just a place to check. And our original code should still work. Okay, so it's not that simple. So now we take a new one. We end up returning -1, even though our answer is at the end. We have 3 over 2, floor is 1, right? 3 does not equal our target, which is 5. Okay, we say if num sub left is less than or equal to target, which it's not, right? So we say if num sub left is less than or equal to target, num sub left, so is 1 less than 5? I mean, is 1, yeah, is 1 less than 5? It is. Right, now I'm noticing maybe all we really ever want to do is move left. Or maybe not, right? Else if num sub left, if 1 is ever less than 5, then we do right equals mid minus 1. Which doesn't quite make sense. Right equals mid minus 1. So now we can only choose between 1 and 3, and we can never really get there because we've cut our potential values off. So I don't think we can really ever move the right side down because we never really know. So num sub left is less than or equal to target. If that's the case, it is not that simple. If so, we have 1, 3, 5. Num sub left is less than target. It's less than or equal to target. Now, if we have the else, we'll say left equals mid plus 1. Left equals mid plus 1. And left, mid is going to be 1. Left equals mid plus 1 would actually make this 5. So I know in the regular binary search you can get away with just 2 loops, I mean 2 cases. Maybe we need to be a little bit maybe we don't have to move them separately of each other. Maybe we can move them both at the same time. So we're saying if num sub left, right, is less than or equal to target, then we don't know how much to move up, right? So maybe we can move right in this case. So what if nums, right, is greater than, so let's just go to the other case, right? Let's say we don't want to move left, right? 1 is less than or equal to 5. Well, let's check right. Is right greater than or equal to 5? So I think it's the equal that's kind of throwing us off here. Is right greater than or equal to 5? I wonder if we go backwards from here and we'll do it like this, then we can actually do left, mid, and right. And we'll say for const idx of left, mid, and right, if any of them, right, IDX equals target, then return IDX. I think that actually would help us here. So it doesn't actually help us here. We still return -1. We're looking for 2. So that was not very clever. Seven, 8, 1, 2, 3, 4, 5, 6. So how is this burning us? We create left, which is 7, right, which is 6, and then we'll say if num sub left is 7 less than or equal to 2, no. 7 is not less than or equal to 2. And if that's the case, maybe we can check our midpoint. We'll say, okay, is 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3. So we'll say 2. Is 2 less than or equal? Is 2 less than or equal? Oh, so this is another way we can do it. We'll say if is 2 less than or equal to our value. Now, if that's the case, we actually can not move right, but we'll actually move. So if is 7 actually, I'm thinking of change. What if we used? I think there's definitely something here with this binary search approach, right? We could say is 7 less than or equal to 2? It's not, right? Then we can check mid. We can say is mid less than or equal to 2, right? And if it is, and that's our new left, basically. And that is how we could do it. And then our new left would actually be this, and then we could say, okay, num submit equal to target. It is, right? And if we do the same thing here, we could say, okay, is 1 less than or equal to 5? Yes, it's 3 less than or equal to 5, then we can actually move 3 next up to here. Check if this works with our original value. If we have a 0, we'll say is 4 less than or equal to 0? No. And we'll say 7 less than or equal to 0? No. So in those cases, we still want to move to mid +1. Now let's try for 3. We'll say is 4 less than or equal to 3? No. Is 7 less than or equal to 3? No. Move to mid +1. So what if we try that version, and then if that doesn't work, we'll try recursion. So say if num sub left is less than or equal to target, then we'll say left equals mid +1. Then we'll have another if, right? Because we could still do even better, right? We'll say if num sub mid is less than or equal to target, then left equals mid +1. Right? And then what we can do is will be pretty close, right? So we'll be at 0, right? And I think what we want to do is actually search for 2, right? So is 4 less than or equal to 2? No. Is 7 less than or equal to 2? No. If it is less than or equal to 2, then we... So if it is less than or equal to 2, so it's 1 less than or equal to 2, then you'd still want left to equal there. Yeah, so if it's less than, so if 4 is not less than or equal to 2, so you actually want to say is if it's greater than, then left is equals to mid plus 1. And then on the right hand side, we could say if right is not, if right is greater than, so at this point we'll have, for example, we're searching for 0. We'll say is 4 greater than or equal to 0? It is. And so we'll say left is equal to mid plus 1. We could have passed the number we're searching for, so that doesn't necessarily work. I think what we actually want to do is use recursion instead completely, and it would start with 2 values. So we could take our recursive, we could take our start, right, which would be a range, and we'd start with these 2 ranges here, right? And this recursive function would check both of these ranges and say, okay, how about is 0 between 4 and 7? No. If it's not, then it must be in the other subarray, right? And so we'll do find of nums with left equals 0 going to nums.length minus 1. And this is what we'll actually return. All we'll really need is a function find with nums number array left, which is a number, and right, which is also a number, and it's going to return a number. And so the goal here is to say, hey, if num sub left, right, is num sub left, because we want to check if 0 exists in this range. So to do that, we'd have to say is 0, so we need to pass our target, right? I'm going to say if target, right, is greater than or equal to nums sub left. So in this example, is 0 greater than or equal to 4, right? And is target less than or equal to nums sub right? If so, then we actually want to do return a find, right, of nums right left, and a new midpoint, which we can calculate as left plus the math dot floor of right minus left over 2 right with our target. Else we want to do the complete opposite, and we actually don't even need an else case. We'll just do it like this. We'll do return a find nums right. The new left is actually going to be right, and then the new left is actually going to be this new midpoint that we calculate. It'll be the math dot floor of right minus left over 2, and we could calculate this midpoint at the beginning, so as to save time. And then we're going to do our right, which is the same, and our target still. And then if we'll have a couple ifs, right? If nums sub left, and we only want this to run, all right, if left is less than, or if left is less than or equal to right, that's gonna encompass this whole thing, right? Otherwise, as soon as left is not less than right, we're gonna return -1, right? And if left is less than or equal to right, then we want to make sure if nums sub, and we'll just calculate the midpoint, right? We'll just say math.floor, right, minus left over 2, right? And we'll just do left plus, then remove all the extra ones we calculated. And then we're going to say if nums sub mid equals target, right, then return mid, right, and then you'll have the else if, and then the else. So let's see if it works for this example. So our call stack is being exceeded. Oh, well, since we still end up, I don't know, we still call it a return and return here, right? If we make it down here, then we do want to check if those values make sense. So we're calling for our original range between 0 and 3. So 1, 3, 5, and we're searching for 5. So 0, 1, 3, right? The first range between 0 and 2. 0 is less than 2, we calculate midpoint. 2 minus 1 is 1 over 2 is 0.5. Floor to 0 plus left is 0. Num sub 0 equals target. It doesn't, right? But is target greater than or equal to num sub left, right? So is 5 greater than or equal to 1? Yes. And is target, is 5 less than or equal to right, which is 5, which is well, it is. So I see why we're struggling. I see why we're getting stuck there. So let's actually bring it back to our original example, because I think we can fix that. Let's see if it works with this example. Oh, the output we're looking for is 0 here. Okay, so if that's where we get stuck, then the way we can fix it is just by making sure that if, and how many nums always has at least one value in it. So we'll just check, right? If nums dot length, right, does not equal 0, right? And right, nums sub 0 num sub 0. And I think this actually could be also fixed by moving our greater than or equal thens, because it wouldn't, and then we could move to our end. So it's actually, what if I uncomment this out? I actually just remove our equal thens here, which would take off that extra case. And then we can try 1, 3. So our call stack is still exceeded. That is interesting. So I'll add those back in. I wonder why it's still going over and over though. So we check, oh right, it continuously equals the value. So I think we need a way, right? And then we had this earlier, so maybe this is just what we need to do. So if num sub mid equals target, right? Or if num sub left equals target, then return target. Then return left, right? And if num sub right equals target, right? Then return right. So we're looking for 3, and we also end up in an infinite loop here. So our range is going to be 0 and 1, 2, 3, 4, 5, 6, 7. So our floor is going to be 3, 0, 1, 2, 3, which is 7, right? Calculate our midpoint. Do any of these equal 3? No. Then we check if target. So is target greater than num sub left? Yes. And is target less than num sub right? Right. And so other problem here, we actually do need those equal signs now that we're checking for these particular cases. Otherwise, we end up defaulting to the right-hand side. We still exceed the stack. So 0, we're looking for index 3, right? And if left is less than or equal to right. Interesting. I see. So we just keep going. They're in mid, right? So what is our else case here? So we change the else, we still go into it, right? But it's if left is less than or equal to right. So if left is less than or equal to right, so we change to equal, right? Is 3 greater than or equal to 4? No. So we do find mid, which is going to be 7, right? Right, we're not moving it forward at all. So that's also probably why we're going infinitely. We don't want to pipe it directly back into mid. Like in a binary search, you want to do num sub left to mid. We already actually checked mid. We don't want to check it again. So we can actually subtract 1 here. And since we'll always check if left and right, we actually don't need these equal signs here. We can actually do mid, right, plus 1, because we already checked it up here. So if I run it for the original test case, we should still be good. If I run it for this one, okay, so we're still running into a problem. Will be output -1, and we're looking for 5. Is 5 greater than 4? Yes. Is 5 less than 7? Yes. So now we're going to check between left, which is 0, and mid -1, right? And mid is going to be 2, right? So we're going to check any of these equal 5, which mid, what this one should actually be triggering, but it's not. So at 4, 5, 6, 7, that's 4 plus 3, so 7 over 2 is 3.5, right? Which means our mid that we calculate is index 3. 0 is less than 7. 7, there's 7 elements, but the last index is actually 6. 6 over 3 is 3, so 0, 1, 2, 3. 0, 1, 2, 3. So at 3. And does 4, 7, or 2 equal 5? It does not. So then we check if target is greater than, so is 5 greater than 4? Yes. Is 5 less than 7? Yes. So we do the return of nums going from 0 to mid minus 1, which is 2. So 0 to 2, looking for target. So 0, 1, 2 should say if num sub mid equals target, which it should, but it doesn't. We end up returning -1. So let's actually check. So it goes 0, 6, but we actually don't go left. We actually go to 4, 6. So is from there we go to 4, 6. So we're going right somehow. So somehow 5, saying is 5 less than, we're just gonna print the target and do left, right, and then nums sub left, right, and then nums sub right, as well as target. So you have 0, 4. So maybe left and right is actually confusing. So our left says 4 and our right says 2. We say is 4, is 5 greater than 4? Yes. Is 5 less than 2? No. So then we end up going right. But we don't want to check on the entire bounds of the array. We actually want this to be mid. Change it to mid. Right, and we actually have this problem where I see why this isn't working. We check if 1 is greater than 5. No. Or we could have another case where we say, okay, it's not greater than 5. If it's greater than 5, then we'll keep it at 5, right? And where we have to move is right. This kind of goes back to the original binary search, except the cases are different. And if it's less than medium, we actually want to move right. The mid, we actually move right equal to mid.